In the darkness between the stars, where the fabric of reality is stretched to its limit, there lies a silent invitation, one whispered by the most enigmatic objects in the cosmos: black holes, the great cosmic abysses, where matter and light are devoured, and the laws of nature are rewritten in the presence of unfathomable gravity. For centuries, they have haunted the imagination of poets and physicists alike, beckoning with their mystery and their promise of hidden knowledge. Now, as the 21st century unfolds, a new breed of astrophysicists dreams of sending a mission, an emissary, no larger than a grain of rice, directly into the jaws of a black hole. Can such an impossible voyage become a reality? And what might we learn, threading the needle between annihilation and revelation at the very edge of spacetime? The story of humanity's encounter with black holes begins not with the roar of rockets, but with the whisper of equations. In the early 20th century, as Albert Einstein inked the final lines of his general theory of relativity, he could not have foreseen the doors he was opening. The equations themselves, beautiful and terrible, predicted that, under enough mass and pressure, space and time could collapse into a singularity, an infinitesimal point where curvature becomes infinite, and the universe's rules break down. Yet Einstein, ever cautious, dismissed such possibilities as mathematical curiosities, far from the realm of stars and galaxies. But the universe is bolder than even its boldest thinkers. Within months of Einstein's 1915 publication, the German physicist Karl Schwarzschild, serving on the frozen Eastern Front of World War I, derived an exact solution to Einstein's equations. His solution described a point mass so dense that nothing, not even light, could escape its grip. The first mathematical portrait of a black hole, though the term itself would not be coined for another half-century. Schwarzschild's radius, the event horizon, would become a boundary shrouded in paradox, an edge beyond which all communication with the outside universe is forever severed. For decades, black holes remained mere theoretical oddities, the playground of mathematicians and the fuel for science fiction. Yet, with the dawn of the space age and the proliferation of increasingly powerful telescopes, evidence began to mount that such monsters truly inhabited our universe. Quasars, radio-bright beacons at the hearts of distant galaxies, were among the first clues, their prodigious energies hinting at engines powered by the feeding of supermassive black holes. X-ray binaries, where invisible companions siphoned matter from doomed stars, offered further hints. It was in these subtle, indirect dances of gravity and light that astrophysicists caught their first glimpses of the cosmic abyss. It took the patient accumulation of decades, of data, theory, and technological leaps, for the shadowy outlines of black holes to solidify into scientific certainty. In 2015, the LIGO Observatory in the United States detected gravitational waves, ripples in space-time itself, emitted by the cataclysmic merger of two black holes over 1 billion light-years away. For the first time, we heard the death cry of cosmic giants, not with eyes, but with instruments attuned to the trembling of the very fabric of the cosmos. And in 2019, the Event Horizon Telescope, a global network of synchronized radio dishes, unveiled the first direct image of a black hole's shadow, the glowing ring of superheated matter swirling around the supermassive black hole in the galaxy M87, 55 million light-years from Earth. The shadow was not merely a picture, but a vindication. Einstein's equations, written in the quiet of a patent office, had described a reality more spectacular than fiction. Yet even as these triumphs cemented the existence of black holes, they deepened the mystery. For black holes are not only astrophysical objects, they are laboratories where the known laws of physics are pushed to their breaking point. At the event horizon, gravity is so strong that time slows to a crawl, and quantum effects, the flickering uncertainty of the subatomic world, begin to clash with the smooth geometry of general relativity. Here, in the firestorm of accretion disks and the silence of the singularity, lies the frontier, where our understanding falters. To truly grasp the nature of black holes, to test gravity itself at its most extreme, we would need to get closer, much closer. For decades, this seemed as impossible as flying into the heart of the sun. Spacecraft, even the most robust, would be torn to atoms by radiation, crushed by tidal forces, or lost forever beyond the event horizon. But the march of technology is relentless, and in the laboratories of Earth, a revolution has been quietly taking shape. Imagine a spacecraft, not the behemoths of Apollo or Voyager, but a wafer-thin chip, no larger than a postage stamp, bristling with sensors, cameras, and a miniature brain, propelled not by chemical rockets, but by the pressure of light itself, a laser beam, spanning kilometers, focused like a cosmic spear. This is the vision behind the Starchip, or Nanocraft, a concept championed by the Breakthrough Starshot initiative and physicists like Avi Loeb and Philip Lubin. These nanonaves, massing mere grams, could be accelerated to a significant fraction of light speed, traversing interstellar distances in years, not millennia. At first, the goal was to reach Alpha Centauri, our nearest stellar neighbor, a mere 4.37 light-years away. But as the technology matured, bolder minds began to ask, why stop at stars? Why not aim directly at a black hole? Could we send a flotilla of nanonaves to the heart of darkness, to orbit, and perhaps even plunge toward the event horizon, gathering data never before possible? The technical challenges are formidable, bordering on the mythic. A mission to a black hole is not simply a matter of pointing and shooting. The nearest known black hole, V616 Monochromatus, also known as ASO 62000, lies over 3,000 light-years away. Even if we could accelerate our nanonave to 20% the speed of light, a feat requiring a laser array drawing tens of gigawatts of power, the journey would take 15,000 years. But there are closer candidates. The supermassive black hole at the center of our own Milky Way, Sagittarius A, sits a mere 26,000 light-years from Earth, its mass more than 4 million times that of the Sun. For missions of exploration, proximity must be balanced against scientific payoff and against the brutal realities of time, distance, and energy. Suppose, for argument's sake, that we accept the time frame, that we are, as a civilization, willing to plant seeds whose fruit will be reaped by generations yet unborn. The next challenge is navigation. A nanonave, once launched, cannot be steered by conventional means. It must be smart enough to adjust its course using only tiny thrusters or photon sails, guided by the faint whispers of starlight and the gravitational tug of planets and stars. Its sensors must survive decades or centuries of cosmic radiation, micrometeoroids, and the relentless bombardment of high-energy particles. Then comes the final approach, the dance with the black hole itself. Here, the science becomes as dizzying as the engineering. As the nanonave nears the event horizon, it enters a realm where time distorts and space curves into itself. Signals sent home are stretched and weakened, redshifted by the same gravity that bends the paths of photons. To survive even a close pass, the nanonave must skirt the accretion disk, a maelstrom of gas heated to millions of degrees, radiating X-rays and gamma rays. Sensors must be shielded, yet sensitive. Data must be compressed into bursts, beamed outward in the narrow windows where escape is still possible. But what could we hope to learn from such a perilous voyage? The possibilities are as vast as the black holes themselves. A nanonave could map the warping of space-time, testing the predictions of general relativity with exquisite precision. It could measure the polarization and energy of photons, seeking clues to the quantum structure of gravity, perhaps even hints of Hawking radiation, the faint quantum glow predicted to leak from the event horizon. It could test the cosmic censorship hypothesis. Does nature always cloak singularities behind horizons? Or could naked singularities exist, exposing the ultimate secrets of the universe? There is a haunting possibility, too, that such a mission might expose the limits of our knowledge. For all our equations and simulations, we do not truly know what happens at the threshold of a black hole. Does information vanish forever, as classical theory suggests? Or is it preserved in some subtle quantum dance, as Stephen Hawking and others have debated? Could the interior of a black hole be a bridge to another universe, a wormhole threading the fabric of space-time? Or would the nanonave, and all its precious cargo of data, be lost in silence, its final message stretched into oblivion by the infinite redshift? To contemplate such questions is to stand at the edge of knowledge, peering into the abyss. Yet it is here, in the tension between what is possible and what is imaginable, that science advances. The dream of sending a mission to a black hole is not merely an engineering challenge. It is a philosophical gauntlet thrown down to the future, to test whether we are, as a species, willing to risk and to wonder, in pursuit of truths that may outlast us all. The roots of this audacious vision can be traced to the earliest days of black hole theory. In the 1960s, as the concept of the event horizon was solidified by the work of Roger Penrose, John Archibald Wheeler, and others, thought experiments abounded. Could an astronaut survive a journey to the horizon? What would they see as the universe outside aged and faded in a final burst of radiation? These questions, once confined to the blackboard and the mind's eye, now find echoes in the plans for robotic explorers. The idea of nanonaves owes much to the rise of microelectronics and the shrinking of technology. In the late 20th and early 21st centuries, the exponential growth of Moore's law saw processors, memory, and sensors collapse in size and cost. CubeSats, miniaturized satellites launched by universities and startups, proved that meaningful science could be done with payloads weighing only a few kilograms. The next leap came with the development of photonic propulsion. In 2016, the Breakthrough Starshot project, spearheaded by Yuri Milner, Stephen Hawking, and Mark Zuckerberg, unveiled plans for a laser-driven sail capable of reaching Alpha Centauri in just 20 years. The technical hurdles were immense: building a phased laser array, developing lightweight, durable sails, and ensuring data return across interstellar gulfs. But the principle was sound. Philip Lubin at the University of California, Santa Barbara, was among the first to articulate the physics of directed energy propulsion. His papers, dense with equations and engineering diagrams, laid out a roadmap. A ground-based laser array would focus gigawatt-scale beams onto a reflective sail, imparting momentum to a wafer-scale spacecraft. The acceleration would be brutal, tens of thousands of Earth gravities, but the duration, brief. Within minutes, the craft would be moving at a significant fraction of light speed, coasting on inertia for the long journey ahead. Avi Loeb, chair of Harvard's astronomy department, embraced the concept with evangelical zeal, seeing in it the seeds of a new era of exploration. In interviews and op-eds, he argued that humanity's future lay not in massive, slow-moving vessels, but in swarms of intelligent disposable probes, each carrying sensors, cameras, and a whisper of artificial intelligence. Such probes launched in the thousands could hedge against failure and maximize scientific return. Loeb's vision was not merely technical, but philosophical. A civilization worthy of its cosmic address would not shrink from the challenge of interstellar exploration. Yet, as plans for Alpha Centauri coalesced in the public imagination, some within the community began to dream more radically. Black holes, after all, are more than distant targets. They are crucibles of fundamental physics. A mission to a black hole would push every aspect of the Nanonave concept to its limit. The journey would be longer, the environment harsher, the science deeper. But the rewards, if even a fraction of the data could be returned, would be incalculable. The first question is one of destination. The nearest stellar mass black holes, like V616 Monocerotis, are thousands of light-years away, too distant for practical missions, unless we accept multi-millennial timelines. But in 2019, a team led by Kareem El-Badri at Harvard identified a candidate black hole, dubbed Gaia BH1, just 1,560 light-years from Earth. This is close by galactic standards, though still daunting for any spacecraft. Alternatively, the supermassive black hole at the galactic center, Sagittarius AU, offers a vastly more massive target, its event horizon stretching over 24 million kilometers. The choice of target is not merely logistical, but scientific. A stellar mass black hole offers cleaner environments, with less surrounding gas and dust, but a supermassive black hole allows for more gradual tidal forces and longer observation windows near the horizon. The next challenge lies in navigation and communication. A nanonave, once on its way, is a speck in the void, buffeted by cosmic rays, micrometeoroids, and the relentless wear of time. Current spacecraft rely on radio transmissions, but at interstellar distances, even the most powerful signals fade into background noise. Laser communications, with their narrow beams and higher data rates, offer a solution, but require precise pointing and timing. Alternatively, a swarm of nanonaves could act as relays, passing data from one to the next in a cosmic game of telephone, increasing the odds that at least some information reaches home. As the nanonave approaches the black hole, it would be buffeted by radiation from the accretion disk, a swirling maelstrom of gas heated to tens of millions of degrees. Sensors must be shielded, yet sensitive enough to capture the subtle warping of starlight and the polarization of photons near the event horizon. The probe's final trajectory must thread the needle between annihilation and escape, skirting the photon sphere, the region where light itself orbits the black hole, and transmitting precious data in the moments before gravity's grip becomes absolute. What then could we learn from such a mission? The possibilities are as dizzying as the gravitational wells themselves. General relativity predicts that time slows near a black hole, an effect measured by observing the redshift of photons climbing out of the gravitational well. By measuring this effect with unprecedented precision, a nanonave could test Einstein's equations in the strongest fields accessible to observation. Deviations from prediction could hint at new physics, perhaps the fingerprints of quantum gravity, or the breakdown of the equivalence principle itself. Another tantalizing possibility is the detection of Hawking radiation, the faint thermal glow emitted by black holes due to quantum effects near the horizon. Predicted by Stephen Hawking in 1974, this radiation has never been directly observed, as it is drowned out by astrophysical noise in all known black holes. A probe skimming the event horizon, equipped with sensitive detectors, could search for the telltale signature of this quantum leakage, offering a direct test of one of the most profound predictions in modern physics. There is the question, too, of information. According to classical theory, anything falling into a black hole is lost forever, its information erased from the universe. But quantum mechanics insists that information cannot be destroyed, leading to the famous information paradox that has vexed physicists for decades. Recent work by Juan Maldacena, Andrew Strominger, and others suggests that information might be preserved in subtle correlations in the outgoing radiation, a possibility that could, in principle, be probed by a sufficiently sensitive instrument. The prospect of probing the singularity itself, where density and curvature become infinite, is likely beyond any conceivable technology. No probe, no matter how robust, can survive the tidal forces at the heart of a black hole. But by observing the behavior of matter and radiation near the event horizon, we can inch closer to the truth, testing the boundaries where general relativity and quantum theory collide. The engineering challenges are, to put it mildly, daunting. A nanonave must survive decades or centuries in the harshest environment known, shielded against cosmic rays, micrometeoroids, and the searing radiation of the accretion disk. Its sensors must be miniaturized to the extreme, yet capable of measuring gravitational redshift, photon polarization, and perhaps even the tiny fluctuations of Hawking radiation. Its power supply must endure without sunlight, relying on compact radioisotope generators or ultra-dense batteries. Its communications must pierce the cosmic void, beaming data across thousands or tens of thousands of light years. Yet, daunting is not impossible. In 1977, 2 Voyager probes, each the size of a small car, powered by decades-old technology, set out from Earth on a journey to the stars. Today, they are both over 20 billion kilometers from home, still transmitting faint whispers of data. In 2014, the European Space Agency's Rosetta probe executed a daring rendezvous with a comet, matching orbits and deploying a lander onto an object just 4 kilometers wide, an achievement once thought impossible. The march of technology is relentless, and what seems fantastical today may become routine tomorrow. The dream of sending a mission to a black hole is not only a technical challenge, but a philosophical one. It asks us to confront the limits of knowledge and the meaning of exploration. Black holes are, by their nature, places where information is lost, where light itself is devoured, where the very concept of inside and outside breaks down. To send a probe into such a realm is to court annihilation, to risk that all our questions will be swallowed in silence. Yet it is also to assert that the pursuit of knowledge is worthwhile, even in the face of the abyss. There is a poetic symmetry in the use of nanonaves, small, fragile, and fleeting, to probe the most massive and enduring objects in the universe. In their diminutive size lies a kind of humility, an acknowledgement that, before the majesty of the cosmos, we are as dust motes, snatching glimpses of the infinite. Yet in their speed, their intelligence, their collective power, lies the promise of transcendence, the possibility that, by working together, we can pierce even the deepest mysteries. Throughout history, the urge to explore has been entwined with the urge to understand. The ancient Polynesians, navigating by stars and swells, dared the open ocean in canoes no larger than a modern living room. The Apollo astronauts, encased in aluminum and mylar, crossed the void to set foot on another world. In each case, the journey was perilous, the risks great, the rewards uncertain. Yet the legacy is undeniable. New worlds discovered, new knowledge won, new possibilities unlocked. So it may be with black holes. The first missions may be lost, consumed by radiation, or doomed by navigation errors. But each failure will teach, each attempt will refine, until the day when a nanonave swoops past the event horizon, transmitting data in its dying moments. Data that will rewrite textbooks, transform physics, and expand the horizon of the possible. The scientific community is already laying the groundwork for such missions. 2021, NASA's Starlight project demonstrated laboratory-scale photonic propulsion, accelerating wafer-scale chipsats in vacuum chambers. The European Space Agency's LISA mission, slated for launch in the 2030s, will measure gravitational waves with unprecedented sensitivity, mapping the population of black holes across the universe. The Event Horizon Telescope continues to refine its images, probing the fine structure of black hole shadows and testing the predictions of general relativity. Yet the leap from observation to exploration is profound. To send a probe, however small, into the heart of darkness is to embrace uncertainty, to wager that the universe is not only knowable, but worth knowing. It is to accept that our instruments may be incinerated, our data lost, our questions unanswered, but it is also to affirm that the act of asking, of reaching, is itself a kind of victory. Perhaps in the end, the true value of a mission to a black hole lies not in the data returned, but in the act of sending it, in the assertion that even in the face of the infinite, we will not be silent, that even as light is swallowed and time itself distorts, we will persist in our quest for understanding. There is a scene, imagined by physicists and rendered in countless computer simulations, of what a probe would see as it approaches a black hole. The stars ahead are distorted, bent into rings by gravity. Time slows, the universe outside racing ahead and fast forward. The event horizon looms, blacker than black, a hole punched in the fabric of existence. In its final moments, the probe transmits a burst of data, red-shifted, stretched, but not erased. On Earth, centuries or millennia later, a radio telescope picks up the signal, decoding the last testament of a machine that dared the abyss. In that moment, the boundaries of knowledge are pushed back, if only by a fraction. In that moment, the dreams of Einstein, Schwarzschild, Hawking, and countless others are vindicated. In that moment, we glimpse the infinite and are changed by it. The possibility of sending a mission to a black hole, then, is not merely a technical question, but a statement of purpose. It is a declaration that, for all our fragility, we will not turn away from the unknown, that we will risk and dare and dream, for the sake of knowledge, for the joy of discovery, for the hope that, in understanding the universe, we may better understand ourselves. The journey to a black hole is, in a sense, the ultimate expression of the scientific spirit, to ask questions that may never be answered, to seek knowledge that may never be fully grasped, to reach for the unreachable. It is an act of faith, not in any deity, but in the capacity of the human mind to illuminate even the deepest darkness. As the 21st century unfolds, the tools of exploration are changing. The age of massive rockets and grand expeditions is giving way to swarms of tiny, intelligent probes, each a spark of curiosity, a testament to the power of collective effort. In this new era, black holes are not fortresses, but frontiers. The question is not whether we will send a mission, but when and what we will dare to ask, in the silence beyond the stars. In the end, the story of a mission to a black hole is not only a story of physics or engineering or astronomy. It is a story of longing, a longing to know, to understand, to find our place in the vastness. It is the story of a species that, for all its flaws, refuses to be content with ignorance. It is the story of a universe that, for all its indifference, rewards those who seek, who strive, who dare to ask the impossible. As we contemplate the possibility of sending nanonaves into the abyss, We are reminded that the greatest journeys are not measured in kilometers or light years, but in the courage to ask and the will to act. The stars call to us, as they have always called. The black holes wait, silent and implacable, at the edge of knowledge. Let us answer.